So we've kind of gotten an introduction to some of the philosophy behind cryptography, and now we'll actually look at something called symmetric key encryption. So before we get to the actual encryption scheme, I'll just introduce a very common setting that we'll use to motivate a lot of our examples, or a lot of the primitives that we learn. So we have two parties, Alice and Bob, and they want to communicate. So in a very simple example, Alice has some message M that she wants to send to Bob. Okay? And they have this open channel where they can talk on this. But the problem is that in the middle of this channel, there's an eavesdropper. So in particular, Eve is in the middle of this channel, and so we don't want Eve to learn this message. So kind of our motivating question to develop this cryptography is so how can Alice communicate M to Bob without Eve learning M? Okay, so right now what we'll do is I'll show how we solve this this problem using symmetric key encryption, and I'll kind of introduce the syntax of the scheme, and then we'll start talking a bit more about what that syntax actually means. So first off, we're going to assume that both parties have some key K, and this is their symmetric key. Okay. And for now we're just going to assume they have it. Later in the class, we'll actually go through how they could derive the symmetric key. But then the following will happen. So Alice is going to generate this message C. Okay. So what the syntax means is we have some encryption enc, and we're going to give it as input the key K and the message M, and it's going to give us some message C, which we'll call this ciphertext. Okay? And Alice is going to send C over to Bob, and then Bob can basically recover the message by running this decryption algorithm on the ciphertext. Okay? So Alice encrypts her message under the key, sends it to Bob, and then Bob can decrypt the message, the ciphertext, to get the message. Okay? And so this is kind of the syntax for our symmetric key encryption. And so the requirement that we have, or what we'd like, is that this C needs to provide confidentiality. Okay. And so what is confidentiality? So here in this setting, we're going to say that we want C to hide all information about M besides the length. So this is kind of how we'll describe confidentiality for right now. So the idea being that even if Eve sees this ciphertext C, it hides all the information about M, so Eve can't figure out anything about M, except for the length. So then the question you may ask is, okay, why do we need to hide this length? So there's a few reasons. So, why do we need to do this? So for the sake of example, let's assume some static ciphertext size. I'll just use CT to denote ciphertext. And let's say that size is n. Okay. So what I'm saying here is, let's say we don't want the length of M to be leaked through the ciphertext. So then we need some static ciphertext size, right? And so we run into a few problems here. So firstly, let's say we set some n and we need to encrypt a message that's greater than n, right? Well, we can't because we would lose information in the process. So we can't encrypt messages longer than n. Okay. And then on the flip side, let's say that we made our n really large so that we could encrypt, most messages. Well, then the problem is, if I encrypt a small message, I'm using a ton of space to encrypt that message, right? So basically, you know, encrypting small messages is wasteful. And so generally what we'll do is we'll leave the size of the ciphertext up to the application, but we aren't going to reason about it in our encryption scheme. Okay. So now let's get to what a symmetric encryption scheme actually is. So symmetric encryption scheme. And what I'm about to give you, you can think about it as a sort of API. So it may seem a little formal, but the idea is that there's many different ways that we can create a symmetric encryption scheme, but they should all follow this basic API that we lay out. So there's going to be 3 algorithms or 3 functions that each symmetric encryption scheme should have, and then there's 2 properties that the scheme as a whole should uphold. So the first function is called keygen. Basically, when you run keygen, it just outputs some key k. And the requirements that we have on keygen is obviously that the key should be random, right? So oftentimes, these algorithms are just going to flip a bunch of bits and produce some randomness. Sometimes the key may be a little bit more structured, but it should still be random. And if you remember why, because of Kirchhoff's principle, we're basically going to publish everything about our encryption scheme besides the key. And so because of that, the key itself needs to be secret, and so how we generate it needs to be secure. So the next algorithm we have is encryption. And as we saw, this takes a key and a message, and it produces a ciphertext. Okay. And then we have decryption, which takes a key and a ciphertext and produces a message. Okay. So those are our 3 algorithms that we have. And then we have 2 properties that we need to uphold. So the first one is correctness. And so what correctness says is that for every key and for every message that we might encrypt under that key, so for instance, so for every key, for every message, we take some ciphertext. And correctness upholds that decrypting the ciphertext should give us back the message n. So basically all correctness is saying is that we take any key and any message. If we generate a ciphertext, when we decrypt that ciphertext, we should get back the original message. Or in other words, what we're saying is that our encryption scheme needs to be invertible. So anytime we encrypt something, we need to be able to recover what we encrypted. And the final property we have is security. So in other words, what security properties do we want the scheme to have? And this is actually a little bit more complicated because we need to have a way to formally define what security is. So we're going to stop here for now and pick up in the next video.